So this is the last two lectures for this unit. And what I've done is summarize for you in this table all the reactions that you're responsible for, and what you should have already done as we were learning about these reactions was to make 3x5 cars for all of them, so that you could do the forward reaction, and all the reactions are differentiated in your head, so that they're not all swimming around and they all look the same. You want to get to the point where you could give me, if you react this with this, will you get kind of problems right away. Once you master that, then you're able to do synthesis, which is what I'm going to focus on. So this lecture and the next lecture is going to be using all the reactions that you've learned this unit, how to go about preparing compounds of interest. So let me just briefly go over with you this table. What I did was I categorized them according to the broad general topics. So the halogenation reaction, what are the steps, and then the alkylation reactions. You basically have to form an enolate. If it's just a regular ketone, aldehyde, or ester, you need to use LDA to form quantitatively the enolate, and then react with a primary alkyl halide to put the R group next to it. These are the special ones that we learn: malonic ester synthesis and the acetoacetic ester synthesis. All right, and then as far as condensation reactions go, we went over aldol, which is aldehyde. So this is showing you an example of a self-condensation of an aldehyde, but you know that there's a cross aldol as well, but they do the similar chemistry. So in self-condensation, you're using a weak base, so that you have in the pod both the enolate and the unreacted carbonyl, so that you can react with each other in a way, and to form this intermediate, which is beta hydroxy carbonyl. And then if you heat it, then you get the conjugated carbonyl. Claisen, you're doing the same thing, except for you're starting with ester functional group rather than aldehyde ketone. And then microreaction, we went over what kind of nucleophiles add at the beta carbon in a 1,4 fashion to add the nucleophile there, and those are these nucleophiles shown here. The enolate, you have to have double electron withdrawing groups in order for it to do microaddition, and then enamines as well. And we also learned how to make enamines, which this should be a review from Unit 2, but then using enamine as a nucleophile and reacting with an electrophile as shown here. All right. So this column, the middle column, should be a review for you, and this table hopefully summarizes everything in one page, so that you can keep them differentiated. All right. So what you want to focus is the last column, which is you want to be able to look for the functional groups, so that you know what reaction you need to use in order to make those. All right. So remember, whenever we did synthesis problem, your first step was to recognize the functional group, and then the second step is to ask yourself, how do I make these functional groups, right? So that's the step that I'm doing here. So for example, in your product, if you see halogenated carbonyl, so in other words, alpha halogenated, so if you see something like this, then you know that you're going to use an enolate and then a halogen as your electrophile, right? So then in the other products, notice when you're doing an alkylation reaction, what you really see is just the ketone or aldehyde or some kind of carbonyl group is all you see in this. So it could be other functional group as well, not just ketone, but so this would be an example. So if you see just isolated ketone, aldehyde, or ester, you might be thinking about doing an alkylation reaction, all right? And then if these are the special alkylation reactions that you saw, if your compound that you want to produce, it has just a carboxylic acid and that's it, then you want to think about using malonic ester synthesis. If your product has basically an alkylated acetone, so CH3, so it's a methyl ketone, then you want to use the acetoacetic ester synthesis. All right. If you see 1,3 relationship, so these are basically bifunctional. So in other words, you see two functional groups, and they're in the relationship of 1,3. Okay, so for example, if you see beta, which is in the third position, hydroxycarbonyl, when you see these functional groups in this relationship, you should be thinking aldol, because aldol produces that as an intermediate. And if you see an alpha beta unsaturated, so you have a double bond and the carbonyl, but they have to be conjugated, then you know that it's the product of the dehydration of the aldol product, and you get the enol. All right, so that's why these functional groups should trigger whenever you see this or this. You should be thinking aldol in coming up with these products. If you see beta ketoester or acid, so in other words, once again, two functional groups in a 1,3 relationship. So you have the keto group and then an ester or an acid over here, then you're going to be thinking Claisen to produce that. Because if you look at it, that's the product that you produce. All right. Now, if you were to able to do Michael addition, what you get is once again bifunctional, and what you see is 1,5 dicarbonyl relationship. All right. So whenever you see that, you should be thinking that one of the substrate is going to be alpha beta unsaturated to do a Michael reaction. All right. And then enamine reaction is you're not going to be able to differentiate it because you could do it many different ways. But I think if you have to do Michael reaction with a regular ketone, then you should be thinking about making an enamine first and then doing a Michael, because enamine is one of the few ways that will add in a 1,4 fashion, and regular enolate cannot. Remember the limitation? So you're going to have to put in another step in order to make the enamine first and then do Michael reaction. All right. So that's sort of like a review of all the reactions in this unit. And so what you want to be familiar with is starting to recognize these functional groups in a synthesis problem. So I made up 5 synthesis problems for us to do. And in the interest of time, I'm probably going to be able to, go backwards in a retrosynthetic method. Couple steps, but not all the way to 2 carbon or anything like that, right? But I just want to get you started in how to recognize functional groups and how do you work backwards. All right, so keep this sheet right next to you as we do the synthesis problems. So we're going to start out with this one. This is the first one. I'll give you a minute to copy that down. And then what I want you to ask yourself is, as you're drawing them, what functional group do you recognize? And using this table that you have, which reaction would you use to make this compound? So pretend this is like, you know, a really, really good drug for cancer. And your job is to make this compound in the cheapest, most efficient way possible. And how would you make that? All right. So that's what organic chemists, you know, do on a daily basis. They have a target and they try to come up with a way to do this. So first, you have to recognize the functional group, right? So the functional group that you should recognize is, it's not a monofunctional group, but is, you know, is bifunctional. So you've got two functional groups, and the relationship between these two carbonyls is that 1, 2, 3, 4. We have 1,5 dicarbonyl. So in this sheet that you have, notice that 1,5 dicarbonyl is over here. That means we have to do a Michael reaction, right? So that's what you need to think about, okay? So need to do, and if it helps for you to write it out so you could organize your thought, that's fine. So then the question is, which way should we do the Michael reaction? Because you know the Michael reaction has an alpha beta unsaturated enone system. So we could make, there are two ways you could dissect this and come up, and either one will be fine. So let's say you want to react with this enolate, okay? So you're gonna have to choose one of the alpha carbon to be an enolate, right? And make the carbon-carbon bond. So you know that when you do Michael, you're doing a 1,4 addition with some kind of enolate, right? In this example. So if we want this carbon to be my enolate, then we're making this bond right here, right? So the beta carbon will be this carbon where it would attack, which means that it must have had a double bond there. So here's my alpha beta unsaturated. So think forward. So this carbon will attack here, make the enol intermediate, and then that will go back to the ketone system. So that would be one way to make this. Or we could try making the enolate with this as my enolate, which means then that you're going to have the enone system will be over here, right? All right, so I'm going to stop here and then continue on the next